If you live near any body of water, such as the Gulf of Mexico or the Atlantic, you know what it feels like to watch the tropics during the summer and fall during hurricane season. You check the forecasts, you follow the tracks, you watch systems form, strengthen, and sometimes turn towards you. During my time as a TV meteorologist on the Texas coast, I saw that up close. Seasons where one system after another developed in the Gulf, storms that seemed to intensify faster than expected. And like many people who have watched hurricanes over the years, I found myself asking a simple question: is something changing? Because when we talk about climate change and hurricanes, the conversation often surrounds the connection between warmer oceans and the number of tropical systems. But the science tells a more complicated story. It's not just about how many hurricanes form, it's how they behave, how strong they become, how quickly they intensify, and how much rain they produce, as well as how long they last once they reach land. Today we're going to take apart what a warmer world means for hurricanes, not just in numbers, but in energy. Welcome to the podcast. I'm Dr. Mack, and this is the Climate Translation. To understand what climate change might do to hurricanes, we need to start with a simple question. What does a hurricane actually need to form? At its core, a hurricane is a heat engine. It runs on warm ocean water. When the surface of the ocean reaches about 80 degrees Fahrenheit or higher, it provides the fuel storms need. Warm water evaporates into the atmosphere, and that adds moisture and energy. That warm, moist air rises, cools, and condenses into clouds, and in the process, it releases heat. That released heat is what powers the storm. It lowers pressure at the center, pulls in more air, and keeps the system going. The more heat that's released, the more the storm can organize and strengthen. So in a very real sense, a hurricane feeds on the ocean. Now, there are other ingredients too. You need relatively low wind shear, meaning winds at different heights in the atmosphere aren't tearing the storm apart. You need enough rotation from the Earth's spin to help the system organize, and you need a disturbance to get things started in the first place. But without warm water, none of it works. Without the fuel, you can't have the storm. So this brings us to a key connection. The oceans are warming. Over the past several decades, the surface of the ocean, especially in regions where hurricanes form, has been steadily increasing in temperature. And more importantly, that warmth isn't just sitting at the surface, it's extending deeper into the ocean. Now, that's important because hurricanes don't just interact with the very top layer of water. As they churn, they mix the ocean beneath them. In the past, that mixing could bring cooler water up to the surface and could weaken the storm. But when the water is not just warm at the surface, but several meters down, that's less of a cooling effect. The storm keeps having access to its fuel. So when we ask what human-induced climate change is doing to hurricanes, this is the first piece of the answer. We're not changing the rules about how hurricanes form. We're changing the environment they form in. We're raising the temperature of the fuel that powers the system. And when you increase available energy in a system like that, the behavior of storms start to change in ways that weren't always obvious at first glance. Now, it's important to point out that while it's true that warm water fuels storms, and warmer water can be thought of as adding more fuel to the engine, the reality is not cut and dry. A warmer ocean does give you more potential energy, but it doesn't mean every storm suddenly becomes a Category 5 hurricane. And it doesn't mean every season is going to be more active than the last. The Earth system is complex. There are a lot of variables at play. But what we're seeing in the data and in the observations of the tropical oceans is a potential shifting of the odds. In a warmer ocean, scientists expect that storms that do form will have a greater chance of becoming stronger. Over the past few decades, one of the clearest signals scientists have observed is an increase in the proportion of storms that reach the higher categories, such as Category 3, 4, and 5 on the Saffir-Simpson scale. It's not that we're necessarily seeing more storms overall, but more of the storms that do form are reaching higher intensity. And there's another piece of this that's been getting a lot of attention in recent research: rapid intensification. This is when a storm's wind speeds increase dramatically in a short period of time, sometimes 30, 40, even 50 miles per hour in less than a day. From a forecasting perspective, this is one of the most challenging scenarios. A storm that looks manageable one day can become much more dangerous the next. And warmer ocean water, that fuel for the storm, plays a key role in that process. When conditions are right, that extra heat energy can allow a storm to strengthen very quickly, especially as it approaches land, where the warm water extends even deeper. Now, if this sounds familiar, it should, because it connects back to something we talked about in an earlier episode. You can think of the climate system like a set of loaded dice. Climate change is shifting the odds towards larger numbers. At any given roll, you can still get a 1 or a 2. We will still have weaker storms and quieter seasons. But with added fuel, the odds are that a 3, 4, and 5 will come up more often than they have in the past. And when those stronger storms do develop, the impacts can be very different, not just because of the wind, but because of what else they carry with them. And that's the next part of the story, because wind is only one piece of what makes a hurricane dangerous. The first thing that comes to mind when you think about hurricanes are their intense wind fields. We think of the structure of the storm, the category, the eye, the images of the strong gusts bending trees and damaging buildings. But for many storms, especially in recent years, the most dangerous part hasn't been the wind. It's the water. To understand why, it's helpful to understand how air behaves at different temperatures. In the classroom, I often explain this using a balloon as an example. If I blow up a balloon just a little, you can think of it as cool air. If I blow it up a lot, you can think of it as warm air. And just like the available space in a balloon is greater when it's larger, warm air has a greater capacity to hold moisture than cool air does. In fact, for every degree Celsius the atmosphere warms, it can hold about 7% more water vapor. Now, that may not sound like much, but across an entire storm system, it adds up pretty quickly. Now think about what a hurricane is doing. It's pulling in warm, moist air from the ocean, lifting it upward, and then releasing that moisture as rain. So if the atmosphere is holding more water to begin with, the storm has more to work with. More moisture in the air means the potential for heavier rainfall. And that's what we're observing. Many recent hurricanes have produced extreme rainfall totals, amounts that overwhelm drainage systems, flood neighborhoods, and linger longer after winds have died down. And another variable to consider is speed. Not the wind speed in the storm, but how fast the storm is moving. In some cases, storms are slowing down as they approach land or move inland. And when a storm slows down, it spends more time over the same area. That means that any given area gets much more rain than it would if the storm was moving faster. Rain keeps falling hour after hour, sometimes day after day. So now you have a system that can hold more moisture, which releases more rain, and it does it over a longer period of time. That combination is what turns a storm from a wind event into a flooding event. You can also think of the atmosphere like a sponge. A warmer atmosphere is a larger sponge. It can hold more water. And when a hurricane squeezes that sponge, more water comes out. But if you hold that sponge over the same spot and keep squeezing, the ground below doesn't get a chance to recover. That's when flooding becomes a dominant risk. So when we ask about climate change and how it's affecting hurricanes, the most clear answer we can get is it's increasing the amount of water available to the system. And that's changing what these storms can do once they reach land. So what are scientists actually seeing in the data? This is where the story becomes more complicated, but more interesting at the same time. When researchers look at the long-term record of hurricanes, especially in the Atlantic, one of the first challenges is the data itself. Before satellites became widely available in the 1970s, we didn't see every storm. Some systems just stayed out to sea. Some were never recorded. So when scientists try to answer whether hurricane numbers are increasing or if the intensities are going up, they have to account for what they may have missed. And when they do that, there are different approaches that can lead to different answers. Some studies that correct for missing storms suggest that over the historical record, going back to the 1800s, there really isn't a long-term increase in the total number of hurricanes. But other approaches look at the problem differently. Instead of counting individual storms, they look at the environmental conditions that produce hurricanes: ocean temperatures, atmospheric moisture, instability. Those studies show conditions that favor hurricane development have become more favorable over time, and that leads to stronger storms. In fact, some research has found what it describes as unequivocal increases in Atlantic tropical cyclone activity when looking at those underlying conditions rather than just the raw storm counts. So now we have two independent ideas side by side. The total number of storms may be uncertain, partly because of the limits of historical data, but the environment those storms are forming in is clearly changing. And there's another layer to consider. Since the 1970s, when we had more reliable satellite observations, many key hurricane metrics have increased. The number of named storms, the number of major hurricanes, and something scientists call accumulated cyclone energy, which is a measure of the total energy produced by storms over a season. Researchers point to a combination of factors behind that increase. Cleaner air, for instance, has reduced certain types of pollution that used to reflect sunlight and cool the ocean slightly. With fewer of those particles in the atmosphere, more sunlight reaches the ocean's surface, and that contributes to warming. Obviously, warmer oceans are more favorable for hurricane development too. So when we ask, are there more hurricanes? The most honest answer is, we're still working that out. But if you ask, are the conditions for hurricanes becoming more favorable, and will the storms that do form be likely stronger? The data is pointing to yeah. So what does that leave us? When it comes to hurricanes, climate change isn't giving us a simple answer. It's not a straightforward more storms or fewer storms. Instead, we're seeing a shift in behavior. Storms that can strengthen more quickly and carry more water. Storms that in some cases can linger over the same area for days at a time. And all of that comes back to something we've talked about throughout this episode: energy. Hurricanes don't operate in isolation. They respond to the environment around them, and the environment is changing. The oceans are warmer. The atmosphere is holding more moisture, and the system as a whole has more energy to work with. That doesn't change what any single storm will do, but when you look at the whole system, it does change the range of what's possible. The story of climate change isn't just about temperature. It's about how energy moves through the system and what happens when that flow shifts. For hurricanes, that means we're not just watching how many storms form, we're watching how they behave. It's an active area of research, and we're still continuing to study how these patterns are evolving, what signals are strongest, and what the uncertainties mean. So for now, the next step is just to pay attention and see where the trend lines are heading, but to prepare for surprises that may come in a warmer world. I'm Dr. Mack, and this has been the Climate Translation. If you have a question about the climate you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.